Hello students, in this video we'll prove Binet's formula for the Fibonacci sequence. Let's recall the Fibonacci sequence is a recursively defined sequence defined by f sub 0 is equal to 1, f sub 1 is equal to 1, and then f sub n plus 1 is equal to f sub n plus f sub n minus 1, as long as n is bigger than or equal to 1, right? N bigger than or equal to 1. This will allow me, for example, to find n. If I plug in n equals 1, I get f2 is f1 plus f0, so f2 is going to be 2, then 3, then 5, then 8, etc., right? These exhibit a tremendous number of awesome mathematical properties. They occur in pop culture all the time, sometimes right, sometimes wrong, but they're really very powerful, and it's an interesting sequence to study. Now, what we're going to do is the following. We're going to observe the following. I can write this as a matrix equation, right? And so I'm going to note that if I look at this vector over here, fn and then fn plus 1, what fn is, and I'm going to assume that n is bigger than or equal to 1 for this. Fn is just itself, fn. And then fn plus 1 is what? Is fn plus fn minus 1, right? So I'm going to write this in the following way. I'm going to write this as the matrix 0, 1, 1, 1, and then fn minus 1, fn. Okay, let's check to see if this works. So I do a 0, 1, fn minus 1, fn. That gives me fn. Great. And then I have an fn minus 1, fn, so this works out, right? Now, the cool thing about this is I can iterate this procedure, right? So if I do this one more, if I do this, I can write this again. This is equal to 0, 1, 1, 1, and then this will be a 0, 1, 1, 1. And I decrease the index by 1, fn minus 2, fn minus 1, right? And if I do this n times, right? So if I do this n times, we see that this is going to be this matrix over here to the nth power. And if I do this n times, I get back down to f0 and f1. I know what f0 and f1 are, right? So in other words, I know I can find a formula for fn if I can compute the powers of this matrix over here. So we have a tool for that. That's diagonalization. So let's diagonalize that matrix. So now let's consider our matrix over here, A. And so I'm going to find the eigenvalues of A, determinant of negative lambda, 1, 1, 1 minus lambda is equal to 0 as the eigenvalue equation. And this is going to give me what? This is going to give me a lambda squared and then a minus lambda, and then a minus 1 is equal to 0. This is a very famous quadratic equation. This is going to be the golden ratio. This tells me that lambda is equal to 1 plus or minus root 5 over 2. So I'm going to call those lambda plus minus with the obvious connotation. Of course, lambda plus for the golden ratio. Okay, so lambda plus the golden ratio. Great. Alrighty, and of course we can check easily the eigenvectors. V plus is going to be 1, and then lambda plus, and then V minus is going to be 1, and then lambda minus over here. Okay, of course we can just check that because if I plug in, for example, lambda plus into this thing, and I hit with 1 lambda plus, I'll get 0, 0. If I do a lambda minus, I'll get a lambda minus with a negative sign plus lambda minus, I get 0, 0. So now I can write down the factorization of our matrix. Our matrix, therefore, 0, 1, 1, 1 is going to be equal to P, which is going to be a 1 lambda plus, 1 lambda minus, and then times lambda plus, 0, 0 lambda minus. Then the inverse of this matrix, so I flip the diagonal entries, like so, negate the off diagonals, and then divide by the determinant, and the determinant in this case is going to be lambda minus and then minus lambda plus. Let's check what that is real fast. So what is lambda minus lambda plus? So I would have a 1 minus, that's lambda minus lambda plus. It's going to give me what? So that one has to cancel out, you can get a negative root 5. So I divide by negative square root 5 over there. Excellent. And of course, now if I raise this to the power k, the beautiful thing about this diagonalization procedure is that we can raise things to the power k. All I need to do is say, if I raise this to the nth power over here, this is going to be an nth power over here and an nth power over here. So that's the diagonalization trick that we could do over there. Great. And so now what do we have? And so now we're in a great position because now we have that fn plus 1 is going to be 1 lambda plus, 1 lambda minus, and then this matrix over here, lambda plus to the n, 0, 0, lambda minus to the n, right? And then it's going to be this matrix applied to the initial vector over here. So this matrix over here is going to be a, I'm going to write this as a, leave the negative root 5, negative lambda 1, positive 1, positive lambda plus, negative 1 over root 5, applied to the initial vector, right? Applied to the, I did this n times, and so I had to apply this to the initial vector. That's going to be a 1 and then a 1. So we're going to have a 1 lambda plus, 1 lambda minus, and then what? Then lambda plus to the power n, 0, 0, lambda minus to the power n. And then what we get over here in the first entry. So everything's going to be divided by root 5. I'm going to put that at the very end. The first thing we get is going to get a 1 minus lambda minus, 1 minus lambda minus, and then we'll have a 1 lambda plus minus 1 over square root 5. Okay. Now again, let's simplify what these things are. What is, if I did, for example, 1 minus lambda minus, that'd be 1 minus root 5 over 2, right? And so, of course, what's that going to be? That's going to be like a 2 over 2, so that's going to be a 1 plus root 5 over 2, right? Because that's 2 over 2. 2 minus 1 is going to be a 1, and then negative 5 is about, so that's going to be lambda plus. Great. And then if we did lambda, so this thing over here is actually just lambda plus. So right over here we have a lambda plus. And then if we did the other one over here, if I did lambda plus minus 1, so if I had a 1 plus root 5 over 2, that's my lambda plus, minus 2 over 2, then what we're going to have is what? We're going to have a negative of what? That's going to be a negative 1 plus root 5 over 2, right? And that's a negative lambda minus, right? So this thing over here is negative lambda minus. Over the square root of 5, right? Excellent. Great. And so now what do we have? And so now we just want to figure out what the formula for Fn is, okay? So what's that Fn formula? All right. So we're going to have this, let's do it. So now the formula for Fn, so if we isolate the first column over here, so if we write this as a combination, this is going to become what? This is going to become a 1 over root 5. So if we look at the first entry over here, Fn is going to be a 1 over root 5, 1 over square root 5. That comes out in front of everything, right? And then what? So if I do the first, I'm going to do the first row of this thing, that's going to be a lambda 1 plus, and then a lambda 1 minus with a negative sign. So I'm going to get a total of what? And so that's going to be hit with lambda 1, right? So if I hit that with lambda 1, I'm going to get a lambda 1 plus, and then a lambda 1 minus with a negative. So these things, if I do this operation over here, this becomes what? This just becomes 1 lambda plus lambda minus, and then these things to the n plus first power. So lambda plus to the n plus 1, and then minus lambda minus to the n plus 1, like so, over root 5, of course, over the square root of 5. Great. And so now this is going to be what? So now I can figure out that if I do the first entry over here, that's going to be my Fn entry. It's going to be what? It's going to be sigma. It's going to be Fn. It's going to be lambda plus to n plus 1. Lambda plus to the n plus 1. And then minus, there's the minus sign right over here. Minus, of course, 0, 0 everywhere. Minus lambda minus to the n plus 1. And this is the Binet formula for the Fibonacci sequence. So now we can unpack this and write what this actually is equal to. So if we unpack this, we can show that Fn is 1 over the square root of 5. Not much we can do about that. Then it's lambda plus, so it's going to be 1 plus root 5 over 2 to the power n plus 1. Minus 1 minus root 5 over 2. That's the negative to the n plus 1. Okay? So the remarkable thing is that this is an integer valued sequence over here. And so this integer valued sequence, this natural number valued sequence, can be represented with these root 5s and these golden ratios over here, which is a beautiful, beautiful formula. And this, as we alluded to, is called the Binet formula. So this is the Binet formula for the Fibonacci numbers, right? And oftentimes it may not seem like this is very useful, but it gives you really cool results, and it helps you evaluate certain power series very quickly and get certain recursion relationships or other sort of generating functions. It's a very, very powerful tool in the study of the Fibonacci sequence. Thank you very much.